Projectile motion refers to the motion of an object that is moving up and to the side at the same time. Imagine you have a rock and you toss it up and to the side at the same time. You're going to see it elevating up and drifting to the side at the same time. So you can see that this is not a straight line, and our formulas from kinematics from one dimension are not sufficient to describe this motion. The good news here is that the motion is actually locked up within a plane. So all we need to do is keep track of two dimensions. One axis, we'll use the vertical axis to track its vertical motion, and then another axis for the horizontal direction to track its motion along the back and forth direction. So let's analyze this motion here, and let's focus first on how the object moved along the x-axis. We can actually go along the graph here and measure the distance between the subsequent locations, and then we will see that they're always equally spaced. On this diagram, they appear to be spaced by 0.5 meters. So here you can go along the positions and you'll find out that no matter where they were, the spacing was always 0.5 meters. In other words, the object must have been drifting at a constant speed along the horizontal direction x, or we will say it had zero acceleration along the x. Now let's look at what happens along the vertical direction. As the object climbs up, we can see that the distance actually between the adjacent positions decreases. So any subsequent position is not as far spaced as before, up to a certain point, of course. Somewhere here at the top of the flight, you can see that the object almost hovers there for a very brief instant there, and then it begins to fall again with the spacing increasing between the vertical positions. So this is very similar, and we recognize actually the motion of the free fall. So we know that along the vertical direction, the object, whatever we throw through, must be undergoing a free fall motion, for which we already know the acceleration, which is g, 9.8 meters per second squared, pointing downwards towards the center of the Earth. So mathematically, we had our formulas for constant acceleration motion, and along the x, they will still describe the motion along that direction. We have v is equal to v naught plus at. The position x will be x naught plus v naught t plus 1/2 at squared, and then we'll have v squared will be equal to v naught squared plus 2a delta x. Of course, what we notice from the analysis of the motion and on the graph, the acceleration along the horizontal, the x direction, is 0. So once we cancel those terms with the a, we actually have only two meaningful relationships here emerging from this motion. One is almost trivial, that states that the velocity along the x direction does not change and remains constant. So mathematically, we will write that as Vx is equal to Vx naught. The middle equation will give us how the position changes along the horizontal. So that will be x will be equal to x naught plus Vx naught t. Let's look at the vertical direction. Let's see what happens along the y. Once again, we'll have the three formulas from constant acceleration motion, and here again we recognize that we know the acceleration a is going to have a value of 9.8 meters per second squared, and is going to be pointing downwards. So with our standard choice of up to be positive, we can actually rewrite those equations in terms of g. Here I have used subscripts y to distinguish the velocity or the speed of what happens of the object in the vertical direction and the horizontal direction. I remember mathematically it's impractical to use the same symbol for two completely different quantities. So that's why I had Vx before for my formulas for the x, and now for the formulas for the y direction, I will have Vy is equal to Vy naught minus gt. The vertical elevation here, I'm going to use the symbol y for it. No more choices, x or y. I need to distinguish. I will keep I will reserve the symbol X for the horizontal direction, and I will use the symbol Y for the vertical direction in the projectile motion. So for the second formula, I'll have Y is equal to Y naught plus Vy naught, so that's the initial velocity along the vertical direction, times T minus 1/2 gt squared, and the last formula will be Vy squared will be equal to Vy naught squared minus 2g delta Y. Remember, I used to call those equations 1, 2, and 3 when we worked on problems from kinematics in one dimension. Here I'm going to have another set of equations that is emerging from X. In fact, there's only one meaningful equation from that set, and that's the equation that gives us the displacement along the horizontal. So I will be calling it equation 4. Now let's see how we can use these 4 equations to solve problems of projectile motion.